Bismillah ar-Rahman ar-Rahim, wassalatu wassalam ala nabiyyina Muhammad. This is my automatic control project, and it's going to be in regards to the water tank level control system. A water control system is a system designed to regulate and maintain water levels at a certain level. We can mathematically model this system in control theory by implementing water fluid mechanics. So essentially, what this is saying is that if I were to have a storage tank and the height were to equal 1, the control system's job would be to keep this at 1. So we're going to have to make a series of assumptions before we actually start making the mathematical model to make the math easier. So our first assumption is going to be constant density, because water is a liquid with negligible volume change in a standard water storage tank. 2, constant cross-section, meaning that the area does not change, only the height does. 3, the ideal flow. We are going to assume that the given outlet coefficient A accounts for friction and contraction, essentially assuming a steady discharge. So this is what's given to us in the specifications. For an ideal sensor, we're going to assume that there is no time lag between the sensor and the control system. In order for us to analyze the system, we must first develop a mathematical model. We know that the fundamental principle that governs the water level is the conservation of mass, or in other words, the volume rate of change, which is a derivative, equals to Cn, which is the entering water, minus C out, the exiting water. And as we said earlier, we know that C out is equal to Q, which is equal to A into the square root of 2GH, which is why we put this here. And the volume is area into height times H. So if I were to take the derivative of both sides, dV by dt is equal to A. A remains constant because it does not change with time, into dH by dt. So I can substitute this into here. Seeing as the total response is the transient response plus the steady state response, we must find Cn at the steady state value by setting t and the rate of change to 0. So we can solve for Cn and plug in the values given to us in the specifications, and we get Cn of steady state equals 0.2215. Notice that this value here, 0.2215, is between 0 and 25, which was the limit that was provided for us. And if we were to look back at our main function, we would notice that the equation is not linear due to the presence of the square roots of h of t. So h of t to the power of 1 of 2 is not linear. It's not linear. So we can't use the p, pi, or PID controllers on a nonlinear function. So we need to linearize it using Taylor series method by substituting our values. So setting x to h and a to href. So here we have solved for the derivative of f. We got it to be ag divided by the square root of 2gh. If I were to plug in the values that we know, I would get the answer to be 0.1107. I plug this back into my original equation of f of h, which equals 0.2215 plus 0.1107 delta h. So I must plug this back into my original equation. Here we can say that delta h is equal to h minus hss, and delta cn is equal to Cn minus CSS. If we were to plug this into this equation, this would cancel out with this to give me this final equation here. Now we must convert this function to the Laplace domain using the Laplace transform. Now if you remember in chapter 1, the Laplace transform of df of t by dt is equal to s into f of s minus f of 0, which is this. After rearranging, we can get the transform function to equal 1 by s plus 0.1107, giving me a gain and time constant of 9.033. And now that I have found the transfer function earlier in the Laplace domain, I can use, or before I apply the P controllers and the PI controller, I want to analyze how the system behaves without any controller. And this uses it using MATLAB. So this is the plant, this is the EFT, EFS. This is the summing point, and this is the output block, this is the input block, this is a unit step. And as we can see here, the steady state error is high, approximately 0.1, and the maximum overshoot it does not exist because it's a first order system. The overshoot does not exist. However, we can't work with this, so we need another type of controller. So I'm going to add a P controller. To add the P controller, I'm going to get the transfer function. T of s in the closed loop transfer function is equal to Kp, the gain of P, the proportional controller, divided by s plus 0.1107 plus Kp. To find Kp, I must set Ts equals 20. When I want Kp to be less than 20. So I can solve for the TFS equals 4 tau, any first order system, which equals 4 divided by 0.1107 plus Kp. If I solve for Kp, I get Kp is greater than 0.0893. This means that whenever Kp is greater than 0.0893 in this specific system, I'm going to get a time lower than 20 seconds, a settling time lower than 20 seconds. And you can see that here. The settling time is approximately begins here, around 19 seconds. Now here I have added the Kp block, adding 0.0893, same as we did earlier. Now we notice that after adding the proportional controller, we are able to keep the settling time less than 20 seconds. However, the steady state error increased. As you can see here, there's a big difference, approximately 0.5. So to fix this issue, we will add an integral controller, an I controller. And you'll notice here that after adding the I controller, I get a second order system. If I have a second order system, that means I have zeta and omega n. I'm going to assume that the zeta value is 0.707. This is known as the Butterworth value. It's the value at which there's the highest stability. And I want to avoid heavy oscillations. So if I solve Ts equals 4 by zeta into omega n, where zeta equals 0.707 and the time equals to 20, I find that omega n is equal to 0.283 radians per second, which I can find I from as well. So Ki equals 0.078. So after implementing the PI controller into MATLAB, I got the following equation, or the following circuit. Here is my integral gain, Ki. Here is my integrator, and here's Kp. They're going to be added together, then multiplied into my transfer function. Here is the output that I got from my scope. If you notice here, you'll see that the maximum overshoot is 1.31 minus 1, which is 0.31, which is approximately 31%. That's too high. However, the steady state error is nearly gone. It's approximately 0, which is very good. Now, after applying the PID controller and using the PID tuning app feature in MATLAB to give me a KD value, I get a graph that looks like this. The overshoot is very low. The steady state error is also very low. It's ideal. However, we'll see why this doesn't work, why we can't use the PID controller. The PID controller gives us outstanding results. It significantly decreased the maximum overshoot and settling time, although it did not affect the steady state error much. We're now faced with the choice what is the best control to choose in this scenario. While the PID controller did give amazing results, one of the operating conditions of this project is that the control system is able to operate under possible measurement noise. The PID controller cannot do that, so using a PI controller is enough to handle the job. Now that I've chosen the control that I want to use, I can finally optimize the gains that I want. So I can set Ts to 20, like I said earlier, and I know that zeta has to be between 0.6 and 0.8 because that is the best range for stability. I chose the higher range because I wanted to guarantee that there will be no maximum overshoot, just to be sure. So the Ts by 2% criterion, 20 equals 4 by 0.8 to omega n, I get omega n equals 0.25. Plugging these values into the characteristic equation and then comparing the terms with the characteristic equation with the gain, I get Ki is equal to 0.0625 and Kp is equal to 0.2893. Now, I can represent this in MATLAB and you can also see here that the maximum overshoot is 1.07 minus 1, which equals 0.07, which is 7%. And I know that the steady state error is equal to 0. And the settling time is less than 20, meaning that this has completed all my conditions. And now that I have designed a control system, I want to see how does my control system fare when it's given tests. I'm going to give it 3 tests: a reference change, a disturbance, and an actuator limit. So as you can see here, I've given in a unit impulse added after the transfer function. So when u of t equals, u of t is going to give me a unit impulse at t equals to 30 seconds. And it's going to give me, this is in the feedback loop, is a noise disturbance, and within the PID controller itself, I have added a limit from 0 to 25 so that I may see how does the system compare when it reaches the max volume. What does it do? Does it fail or does it not? And as we can see here, the system has passed all the tests. So here we know that the maximum overshoot is equal to 1.04 minus 1, which is equal to 0.04. We can see that the settling time is less than 20 seconds, and the steady state error is approximately 0. So over here on our last slide, we have a chart which shows me how I passed the 3, or how well we passed the 3 tests. So the reference change, what's meant by this is the 0 meter to 1 meter step, the input. How it settled at 1 meter in 18 seconds, so it passes. The disturbance, minus 0.05 meters cubed per second leak at t equals 30 seconds. It rejected this and went back to 1 meter and it stabilized there, so it passes. The actuator limit, the pump capped at 0.25 meters cubed per second and no windup was induced, meaning no stability, so it passes this as well. Bismillah ar-Rahman ar-Rahim. We are now going to start the MATLAB simulation. So here I have the no controller model, and here we just have a feedback loop, simple. And you'll see if we press run, then output, we have a small steady state error around 0.1, but it's still not what we want. We want it to be approximately 0. We don't have a maximum overshoot, but we have a fast settling time. Let's see what happens when we add a KP controller, or a P controller, sorry. There we go. So I've calculated the KP to be 0.0893, and if I press run, output, you'll see that the steady state error increases a lot, as does the settling time, and there's still no maximum overshoot, so this is not ideal. And if we go here to the PI controller, sorry. Yep, here to the PI controller. So we'll notice that the PI controller is in parallel, or the P controller, the I component is parallel with the P component, because they're going to be added together and multiplied into the transfer function. If I press run, you'll notice that I now have a maximum peak of approximately 1.3 minus 1, which is 0.3, yes. And the steady state value has decreased a lot. Whereas before it was 0.46, now it's approximately 1. And the steady state value has gone down, or the settling time value has gone down. Now, if we go to the PID controller, and if I were to disconnect these for now, a smooth output. This would normally be good, but I'm going to explain in a while why this is not ideal. So let's go to our final. Once we set up on the PI controller, these were the values we got for it. And as you can see here, if we press run, output, here are the values we got. So less than 10% maximum overshoot, 0 steady state value, and times settling time less than 20 seconds. So the same as the PID, however, it does not need the D component. Now, what happens? I'll put these functions under a test. So I need the white noise. I need a summing point. I'm going to put the summing point here. I'm going to delete this. So this has to be the other way around, CTRL-R. And here. So this connects to this. And this connects to this. And this is going to go in here. And what else? I want to, let's move this here. I'm going to add another summing point, CTRL-R, rotate, put it here. I think it was 0.001. I apologize. You'll see here that if I press run, and I apologize, I forgot to set the time to 35. If I press run, you'll see here that in the output, it goes through a slight change at time equals 30 because of the impulse, but it slowly goes back to steady state value, meaning that passed all the tests. And all this line you see here, these squiggly lines, it's because of the noise suppression. However, it's still at the steady state value, meaning that everything here is working and has passed our tests.